Alrighty, happy Tuesday again. So we've got some fun today. So we're moving on to linked lists. Now, linked lists are fun, not super practical, I'm going to be honest. There are specific times when a linked list will be fantastic. It'll be a very good tool for your solution. Most of the time it won't be. Right, it depends. So as we start this second half of the semester, essentially, this later part of the content, we start looking into these data structures and their efficiency. We want to talk about what they're fast at and what they're slow at, because different ways of storing data will be faster or slower depending on what we're doing with them. And that's why we're going to spend so much time actually building them so that you can appreciate why they're fast and why they're slow, because you have written one. Will you ever write one in the real world? No, because there are built-in ones in the library we can use. But we're going to take some time and build it so we can appreciate better why it's good at what it does, and that sort of thing. It's going to feel a little tedious, I'll be honest, but that's okay. We'll get through it here. So we're going to do that this week, and then we've got midterm review and the midterm coming up the week after. I'll give you last year's midterm that I gave for this class, because I'm supposed to rewrite them every semester, because not that you folks would do it, but some people like to put them out on websites like Course Hero or Chegg. And Chegg, while they have the ability to keep my questions from being posted for 24 hours, refuses to keep them posted after that, because that's how they make their money. So it's another reason I hate Chegg. They're just awful people. So I'll give you last semester's. I'm going to rewrite the long answer questions, and they'll be perfectly fine. So it'll be half quiz questions, like 15 quiz questions, like just like we were doing from the quizzes, and then 3 long answer, write a little bit of code here. The goal is you could take it in class if I wanted to sit and watch you take a test. I don't want to do that, and not everyone likes taking tests at 9:30 in the morning. Is that a good assumption? So what I'll do is that Thursday, March 21st, I will open the midterm, and as long as you start it and complete it by 3:26, you can pick your 90-minute block that you would like to take this exam in. So it'll still be timed, because that way everyone has the same time amount here, but you take it whenever you like to take exams. So if you like taking exams in the middle of the night, go for it. If you like taking them at noon, go for it. Whenever you've got time between 3:21 and 3:26, I'm good with you taking it then. That's the goal. So again, I don't need to sit and watch you take it. You will agree not to cheat, and I will trust you not to cheat. And if you do cheat, you understand you failed the class. That's been our policy for the semester. So it's not meant to be hard. I don't think hard exams are useful for anything. This is just sort of like a checkpoint. I know we're in the later half of the semester, but we've essentially covered the basics now. So we took 150, we learned a bunch of C++, and the first half, or 2/3-ish or so of 200, we've learned more interesting stuff. Like the linked lists and all these stacks and queues and searching and sorting, that's more advanced sort of thing. It's not like basic C++, how do I do things? This is specific tools and techniques. So this is your checkpoint for, do you feel good with all things C++ after essentially 2 semesters worth of learning how to code, right? So if it feels good for you, good, you should be in pretty good shape. If it was rough, come and talk with me, right? We need to get you set up for more SI sessions, more tutoring sessions. You need to meet with me during my office hours to get you caught up, right? So it's meant to be relatively easy, that sort of checkpoint here. It's not hard, it's not super easy, but it should be doable if you're doing well, okay? That's the goal for that. So on 3/19, I'll give you the last semester. I'll probably even post it early, maybe Thursday I'll post it for you so that you can look at it, and then we can go over the answers on 3/19. And that's my only plan for 3/19, is just go over the long answer questions for you. We'll still do our lab. I think we'll have enough to do for lab. We can do linked lists today and linked lists 3/19. We'll see how far we get, because there's a lot of stuff to do with linked lists. So we should be in pretty good shape. Yeah, but that's the plan moving forward. Does that sound good? Okay, cool. So let me fire up Visual Studio here. And let's pull up our Zybook, because this is fun, right? So they have not a section on linked lists here. So this is just coming out of notes, right? For linked lists and for stacks and queues. But they use templates. So to do a linked list, it will be a template class. that we're going to be using for this. So we'll use some of those pieces here as we go. All right, let me fire up a new project. This is, what week are we in? Week 10. Wow, week 10. Console app, 10, linked list. All right, so far, the only way we know to list data, put data in a list, is in a standard array, which is in a fixed size when we have to tell it how big it is before we start, or a dynamic array with dynamic memory. That can be a runtime set size, which gives us now, we could ask the user how big it wants to be, or we could go and recreate a new one and make it bigger, but you can do that with the standard array as well. Or we can use a vector. Right, we have those three ways of storing data. All of them are index-based. Right, we say, hey, give me the value at index 3. And then we'll go and count out 3 indexes, right? 0, 1, 2, and 3. So that'll be the 4th item, and return that item to you. So we can instantly get to any value by index because it uses the memory address, right? We spend a little bit of time looking at when you give it a memory address, it just does some quick arithmetic and jumps ahead and reads that value at the memory address. So when you create an array of size 100, you're getting a block of memory the size of 100 integers, or the size of 100 whatever object you have here. Now the fun thing, when we start using classes, right, it needs the memory address the size of those classes. If you use pointers and you have a array or vector of pointers, it needs 100 times the size of a memory address, which with most of our 64-bit systems nowadays, I think everything's 64-bit by now, right? We've got 100 times 64 bits. 64, so that's 8 bytes. You remember bits and bytes? That's so much fun. You'll come back to that in 310. It's entertaining. That's the class we like to joke about, is makes CS students glad they're not electrical engineer students or ECE students, because you start getting into like what hardware level stuff is. And most of us think, oh, that's neat, but we're glad we don't do it day to day. That's my opinion, of course. Would not be interested in doing anything that low level all the time, but it's fun. So lots of bits and bytes. So having that contiguous block of memory, and when we need to get bigger, can be a little bit slow, right? So when we had our vector and it runs out of room, or when we did our fighting pet storage and you had to make more storage, right? We're essentially making a new array, double the size or something, however much bigger we want to make it, and we have to copy all the old items into the new item, into the new array, right? We did that part. So the general strategy for that, to make it not super slow, let me actually draw a picture here. This is super fun to draw a picture. Is usually you'll do some sort of geometric doubling. So if I have room for like 4 items here, I can throw something in spot 1 instantly because there's room for it. I can throw something in here instantly because there's room for it. I can throw something in here instantly, there's room for it. In here instantly, there's room for it. When I go to add a 5th item, there's no room. So in terms of how many items I have, if I double my size, right, I have to now I'll go make 8 spaces here. And I'll just copy 1, 2, 3, 4 things down. So it takes me n number of operations, n being the size of my array. I don't know why we use n, number maybe, the number of items, to copy things to the new array, and then I can start putting in some more things here. I can put in 4 more things. Once this one fills up, I'm going to double again, and I'll have 16 spots, and I'll copy n items down. And then when that one fills up, I'll have 32 spots and copy the 16 down, and on and on and on. What's fun about this is, thanks to not even super fancy math, the idea of averaging that time that it takes to double across. If you imagine if we were to like graph this out here, so if we made a little graph, this is, we want the size here. This is our n, right? So when it's 1, 2, 3, 4, 5, 6, 7, and on and on and on, right? And this will be the time, right? Most of the time it's 1, and then every so often it spikes, right? And then it's 1, and then it spikes, and then it's 1, and then it spikes. And we're doing doubling here, so we're kind of making room for these. So what you can imagine, if you were to average this, take all these bars here and just lay them down on top over here, right? I get 4 fast ones, and then it has to double. So if I average that across the 4 fast ones, it's really each one took 2 operations. And then I get 8 fast ones, and then it has to double. So the 8 that I have to copy, if you lay that one down, right, essentially is double here, 2 operations here. Same with this. So if we do the geometric doubling, we can average that. We call it the amortized average, if you like fancy math words here, right? We'll say, okay, well, essentially the average time here is 2 operations. Okay, and that's actually pretty quick. So in terms of n number of items, on average, it will still be a constant number of operations. So when we look at how fast things are and how slow things are, you get a couple different graphs. So a constant, right, is flat, right, in terms of n items here, and this is time, right? That's a constant, right? You might have a logarithmic growth, right, where we like a nice little log curve, right? It does grow, but it grows slow, right? That's log. And we're going way back to math class here, right? So this is constant. That's a log growth. You might have a linear growth. So the more n you have, linear, that's L-I-N, linear. It's hard to write letters. I should have brought my tablet. I want to bring that sometimes. Linear growth. You might have a n log n. So linear times a log, right? It kind of grows a little bit slower here. N log n. Or you might have more of a parabolic curve, right? Your n squared. That one's real bad. Or even worse than that, it's just like super up high, you get like n factorial or something ridiculous here. So when we look at how fast things are and how slow things are, constant's the best. Because I can have 10, I can have 50, I can have 100, I can have 1,000,000 items, and a constant number of operations based on the size of my n is generally going to be the fastest. Because it doesn't matter how many items I have, and that's huge. So as we start looking at how I can manage millions of pieces of data at a time, I don't want things that take n operations if I've got 1,000,000 pieces of data. That's going to be relatively slow. Now, again, computers are fast. They can do millions of things relatively quick. But in terms of how does that relate to like a constant speed, it's much slower. So the log speed's great. Linear speed, it's not ideal. Right, n log n, so and they just keep getting worse, right, as we go. So n squared or n something. There's a 2 to the n as well somewhere in here. I think it's 2 to the n. I forget which one is worse, factorial 2 to the n. My math is a little fuzzy. They're both bad, right, at some point. I don't remember which one's which. We could look it up somewhere in a table, I'm sure. Thanks to the internet. But those are bad, right? So if we have the array-based notation and we need to increase our size, if we do the right sort of increasing our size with the geometric doubling, we'll get a constant average. So when we talk about performance, there's really 3 measures of performance we're going to look at. You're going to look at the best case performance, which is rarely ever useful because you rarely ever get the best case. So most of the time we say, sure, it's interesting to know, but we forget it. Doesn't matter. You look at the average time, which is the most important one because average should be the average, right? Most of the time you get the average. So that's important to know what the average time performance is. And the other one that's good to know is the worst case time. The worst possible time for adding something is n here, right? Because occasionally we will get an n performance when I have to do my doubling. I'd have to double my size, move n items down to the new array, delete the old array, repoint the new array. Right? The worst case performance is n for this one. But on average, we say it's constant. And the fun thing here, when we do this sort of algorithm analysis, constants all get thrown away. Or, coefficients get thrown away. So, 7 times n is still n. 3 operations is still constant. We would just call it 1. So coefficients essentially get thrown away when we look at these things. Now, they do matter, but in terms of when we analyze these things and compare them, we throw away the coefficients because we don't really care about them. Because sure, like 27 operations for every n is slow, but 27n will be faster than an n squared almost all the time, right? I guess if your n is like 2 or 3, then n squared won't be so bad. But on average, you'll probably have more than 2 or 3 items in your data structure. So very quickly it won't matter at that point. And when we look at all these things, we use a Greek letter. I don't even know what the letter's called, but that's a big O. So we call this big O notation or O notation. What is the big O notation? Performance. Big O. Algorithms. Big O analysis. Let's see. Doesn't even tell me what the letter is. No, I don't. Is it just an O? Is it just O? I thought it was a Greek letter. Yeah, there's. No thank you ads. My goodness. Big O, big theta O, big omega notations. We're not going to worry too much about this. In your data structures algorithms analysis class, that's 350, you'll spend lots of time on this nonsense. That's a bit more of a math heavy class. Thankfully for us, we don't have to do a lot of that complex math, okay? Which is nice. It doesn't matter that much right now. Anyway, so all of that to say, our vectors or our array-based notation, right, will average to constant. Their worst case is O of n, and the best case is constant. We don't really care about best case, but it's constant, right? It's just one operation to add, or two whatever it happens to be. Number of operations to add is great. When we look at linked lists, now we're going to look at a different way to store information. So let me pull up one more picture here. So with a linked list, what we're going to do is we're going to create these things called a node. And the node is going to be a place where I can store some data. That's the actual piece of information I'm storing, and who comes next in the list. So what you might imagine is this is a list of, or if we wanted to make a linked list out of you folks, you would know who comes after you, right? So what we could do is imagine you just need to know who came into the room after you. Whoever came into the room first will be the first person. Their job is to find out who came in after them. And they can look at the doors, whoever comes in next, and then they can say, okay, you came in after me. And then that next person, when the next person comes in the door, can say, okay, you came in after me, and you came in after me, you came in after me, you came in after me. So we could follow these lists, these links of who is the next node here, right? We'll have some data, and we'll have the next. And we can just follow these links. So eventually we could find the last person enter the room, which was me because I was late today, right? Whoever was before me, the next to last person, right, would know that I came after them because that's what they were tracking. And then I would be waiting for the next person to walk through the door to find out who came after me, right? So these nexts here become pointers, right? We point at the next node in the linked list here. So what's cool here is we don't need to have a contiguous block of memory. So if I'm going to store 50,000 items here, I don't need to go out and tell the operating system, hey, give me one giant block of memory enough to hold 50,000 items. Because there's no direct array that we're putting these things in. I'm not putting it one after another in memory. I'm just saying, hey, put a node somewhere. Wherever that node is, I can find it because I have its pointer. I have its memory address. And when I want to make a new node, sure, I'll go make a new node and then we'll point at that one. And I'll make a new node and then we'll point at that one. Right? I will always know which one comes after, and it doesn't matter where these things show up in memory. So if you think about the performance of adding an item here, that's an A, well, I guess it's more of a D, ADD, right? To add to the end or to append, to push back, like we do with the vector, to throw it at the end here, it's always going to be constant here because there's never any resizing. So in the worst case performance of the linked list, to add something to the end is always constant. Because I never will have to do that geometric doubling sort of thing where I have to go copy a bunch of nodes to a new array because they're not in an array. The only limitation I have is when the operating system tells me there's no more memory, which is, again, not super common because we're pretty spoiled with our computers having like 8 to 16 gigabytes of memory, which is a very large amount of memory. Now, eventually it could run out if we're crunching large data sets and things like that, but that's what you have other computers for. And the cloud, which is just a fancy word for someone else's computer. All the cloud is. So performance-wise, this can add a lot faster, which is super cool. And as we look at linked lists, we'll look at other ways we can make it be very fast, very efficient here, which is lots of fun. So to make a linked list then, what we need is a class for the node. So we're going to make a new class here. let's make this our linked list class. Linked list class. So we'll have a class for a linked list, and this is a template type here. So this will be a template of type name T here. Template. Oh goodness, what am I missing here? This is why I can never remember these things. Template, template class. Where'd it go? Template, type name to type. Maybe it's because I didn't finish out the class here yet.
The template was outside the brackets.
Template. Thank you. Yes. All right, perfect. So this will be of type T. So some given type that I can store. Here as I go. So I'll have a private section, private, and I'll have a public section. So with my linked list then, to create a linked list, I need to give it something of type T here. And the things I need to know for linked list, right? I need to know where the first node is. So when you make a linked list, I need to know what the first node is. So I might have and I probably should write my node class in here then as well. So I'll have a class for node. And node is also a template type, type name T. So I'm going to have this inner class, which gets to be a little bit silly. I think it goes in, does that go in the private section? Probably goes in the private section. It's been a little while since I wrote one of these, because again, you don't ever write them by hand. This is just a thought exercise for doing this here. But we're going to make a class for node. Now, I don't want this to be external. I don't want anyone to ever use node. So when you think about this idea of encapsulation and abstraction when we're writing our classes, node exists purely for an implementation of linked list. No person using linked list will ever know that node exists. We're going to hide that detail away, right? With the idea of abstraction and encapsulating all of our details, they don't know that node is there. This is strictly for me to use my class to create it internally for it to operate. So for node then, node will have a T for data. And now really with node being an internal class only, I can just make these things public so I don't have to go through a bunch of hoops with this sort of thing. So I'll have a T for data, and then I'll have a node pointer for next. Right? So the next node in the list here. So the node points to the next node, which points to the next node, which points to the next node. So you point to who came in after you, right? And you point to who came after you. That person points to who came after them. Node will point to the next node in the list here as we go. And then it's usually helpful to have a constructor, right? So I might want a node that takes a T for data and a node pointer for next. And I could probably default this one to null pointer if you don't tell me which one comes next, right? My this data is the data, and my this next is the next. This will just save me a little bit of time creating these things, right? And I think a lot of you are using the colon notation for assigning these values. I haven't gotten on that bandwagon yet, I apologize. Right? You can use your shortcuts to assign stuff with that notation, which is great. I'm sorry I'm doing it the slow way. I don't know, I'm just used to this, my apologies. That's what happens when you get old. You get used to things. All right, so that's node then. So in my linked list then, I will have a node pointer for first here. So I know which node is first in my linked list here. This has to go above it, doesn't it? There we go. Okay, so I'll have my first node, so I know where it starts, right? And then I probably have an integer for number of items or size. Right? I want to know how many items my linked list holds. Like you can ask a vector how many items it has. It's super handy, really useful to know. Just a great piece of information here. Okay, so I've got the first node and I have my number of items. Great. So I should be able to make some functions here. So things we want to do with a list, right? We should be able to add something to it, right? We should be able to get an item out. Right? I'm trying to think of what else we do with vectors. Right? There's not a whole lot to it here as we go. So when we make one of these things, we can either make it so that you can make a linked list with no items, which is a little bit obnoxious because then I have to deal with first possibly being a null pointer as well. Or I can say, when you want to make a linked list, you have to give me the first piece of data. I prefer that because it just makes my life easier. Now with vector, you don't have to give it its first piece of information, right? It will figure it out for you. It's kind of a little bit silly. I don't know. Is it okay if we just make node take a piece of data? Again, this is just for the thought exercise here. So we're going to make a linked list constructor that takes a t for data, right? That's the first piece of data here. So to create this linked list then, I'm going to say this first equals a new node given the data. Right? So I'm going to set my pointer to a new node, right? Creating some dynamic memory, dynamic objects here. So I can use pointers and all that good stuff works for me here. And I'll give it that first piece of data. And then I'll say my number of items equals 1. Right? So I can always add something. Or I start with one item and I've got my first one. So now if I want to add something to my linked list here. Now if I only have first, adding to the end is actually kind of hard because I have to get all the way to the end. So I'm actually going to cheat for a minute and we're just going to add to the front. And the first item will become the last item. And then every time you add a new item, it'll just be the new first item. Is that okay for right now? And then we'll figure out how we can change it as we go. Right? This is some of the exercise with this. So for now, when we have add item, this will be a void add item given a t data. Or should we call it item maybe? I'm calling these items add item. We should call it item, I guess. Doesn't really matter. So what I want to do then, I'm going to make a new first. Right? So this first is a new node. Now node, right, takes two pieces of information. It takes the data and the next node. So it'll take the data, and what comes next then will be currently my first. Right? So I'm changing, my first becomes a new node that has the data and points at what comes after it is what used to be first here. And I'll take my number of items plus plus. So I can add items here. Why, it doesn't like node. Does it not like node? Did I put it in the wrong spot? Goodness. I think it'll work. We'll try it and see. It looks a little bit upset. So I should be able to add something here. So if we had our linked list here then, and we just added some numbers. So just throw out some numbers to me real quick. 2. So we'll add a 2 here. And its next is null. There is nothing after this. This is the only item, right? So this is our first here. Okay? First points at this one, because first is a pointer, points at this one. And we want to add another number. What number do you want to add? 3. All right, so we're going to make a new node for 3. Its next points to this one. We said, okay, you point to current first, and then first, you don't point here anymore. You point over here. Now you're first, right? And we add another number. Are you going to say 4? Okay, 4. We'll add a new node for 4. It points to 3, which used to be first. Then we say, okay, first, you don't point here anymore. First, now you point here. Get the idea? And we just keep on adding and keep on adding, keep on adding, keep on adding as we go. So we can add these things in constant time very easily. Let's see if we can get that running here. So let's include my linked list here. And see if we can make a linked list. So linked list, and we give it 2, right? We said. Linked list of type int. There we go. A list of 2. And then I can take my list and we can call add item. We can add a 3. And I can take my list.add item and I can add a 4. Right? We can't get them back out yet, but we can at least try and make them here. So let's see if this runs. Oh, no build errors. Okay, yeah, it doesn't like. What doesn't it like? Show me my build errors. There it goes. Data. Oh, yeah, that's called item. There we go. So item and item. Let's see if that works now. No? No. Node class template cannot be constructed. Oh, new node of type T. New node of type T. And let me do that. No, node then of type T. Next, there we go. Gotta add all of our T's everywhere. Okay, now it's happier. Look at that. If we do it right, it gets happier. So the linked list of type T has a node of type T next. I gotta make sure I'm passing in that template type everywhere so the node knows what type it is as well. Oh goodness, no. No overload function can convert all the argument types. Really? Node, a node of t pointer? Is that it? I'm getting there, we're getting there. No overload function can convert all the argument types. We have an item of t. We have a node pointer of t first. Node of t first. Come on. Pick up the t here. Cannot convert from linked list node t pointer to linked list node. Did that take care of it with my t? All right. If we add in all the t's, maybe we'll get there, right? So now I can step into if I want. I'm just going to step over for a second. So I see my list, right? Now, first is a node, right? It's memory address. So this like big old long hex string here is the memory address. The next node is here, right? So if I expand this, it actually knows what the nexts are, which is super cool. Eventually I get to a null pointer and it's over. We stopped, right? Cool. So we can find basic linked list here. Now, if I want to get an item out, then, right, we could pop an item off. Right? I think that we have pop. Is that one we used in vector? You ever use pop? So that would give me back a t type here when I pop something off. So pop then will give me an item back, and it will remove it from the list. Right? So I'm going to say my this first. So my t item is first dot data. Right? The first is data. Right? Is the t for the item I'm going to return. So I've grabbed that piece of information. Whatever's in the front, grab the thing it's storing. Then what I'm going to do is I'm going to take my first, and I'm going to say, okay, you're no longer the first one. I need to go to the next one. So it'll be firsts dot next. So change first to become the first next. So when I have 4, 3, and 2, and I want to pop 4 off, I'll say, okay, let me go hold on to the 4, right? Hold on to 4 here, and then change first. First, you're not pointed here anymore. You pointed to my next. So now first we'll move to the 3 here. Right? That takes this one out of the chain, out of the link here. And I can give the 4 back. And I probably want to delete that because I'm allocating new memory, right? So let me hold on to that. The node of t. Look at that. Can we just use auto? Auto old first equals first. I love it. Right? Auto will save you the typing here. And then I can delete old first. Right? Make sure we free up that memory. And then I can return the item. Right? If we're using dynamic memory, we want to make sure we're freeing it up when we're done with it. Right? Give it back to the operating system. Right? We don't want to hang on to it. So make sure we can store it so I can go delete it after I've changed what first is, because I don't want to delete first anymore. And if I delete first before I save that pointer, right? If this gets deleted, I don't have that pointer anymore to change my first to the next item. Right? So the order we do this really matters here. I should be able to pop that item off, right? And then get it back out. And then make sure we take our number of items minus minus. Right? We probably want to just make that a public function real quick. So we have an int, size or something, right? Return number of items. No, number of items. There it goes. Right, that would be pretty useful. Here as we go, to have our number of items. So in my list then, I can say maybe while my list.number of items size does not equal 0. Maybe we see out list.pop and an end line. Oh man, using namespace standard. Okay, so I should be able to output what I'm popping off and then grab the next one, pop it off, go grab the next one. It should work until size is not 0. When size is 0, I stop trying to pop things off, which will go badly for me anyway, because when I don't have a first, right, eventually first will become a null pointer. I guess we have to handle that anyway then for adding items, but if first is null, when I make a new node and I say its next is first, if first is a null pointer, because I've gotten all the way to the end here, like if we go and pop off, so first it was 4, we returned 4, first was 3, we returned the 3, and we pointed now first at 2, and then we gave back the 2, and now we said, okay, first is, this one's next, so first will be a null pointer, right? First is null pointer. When I create a new node here, when I go to add one, first is a null pointer, so the next, first next is null pointer. That's okay, that was our default position anyway, with just one item. So the null pointer means I've gotten to the end, right? So I think this should be pretty happy. So we should get 4, 3, and 2. Oh, we can take my breakpoint off, see if it runs. Does it run to the end without crashing? It runs to the end without crashing, 4, 3, 2. I forgot the hello world. We're very excited this morning. So this is our very basic linked list. We call this a singly linked list here as we go. Now, we might not always want to add to the front, right? Because if you think of like our vector, usually we add to the back, because if you think of a list, usually the order matters here. So what if instead of adding to the front, how could we make it add to the back without it being super slow? So I could go and traverse every link to find where the next is a null pointer. That would get me to the end, right? I can say, okay, let's go to the next node, go to the next node, go to the next node, until your next is null. I know I'm not at the end. When I get to when your next is null, I know I'm at the end. But if we think of how long that takes, right, I have to traverse n links to get there. That's super slow. So can we do something? Sorry, my sugar's a little bit upset. Eating a bag of mini donuts is not good breakfast if you're diabetic. You'd think I know that by now, but it's very tempting, very tempting. So what can we do to shorten the amount of time it takes to get to the end of the linked list? Is there another piece of information we could store, maybe? Right, we're already storing first. What if we just stored last? Could we store the last node? A pointer to the last node? Yeah, that's a good thought, good thought. So we'll have then a first and we'll have a node of t pointer for the last. So when I make a new linked list here, like this last is my first. When I make a brand new one, first and last are the same node, right? Because there's only one item. They're the exact same node. So when I want to add an item, now I don't want to add a new first, right? What I want to do is add a new last. So my this last then will equal a new node. And, well, what comes after it is nothing. But how do I make sure that last knows what comes after it? So if I had 4, 3, and 2, how do I put something here, right? Like a 7. Well, I need to tell. So we would, in this case, right, first would be 4, last would be 2. So I would need to tell my last it has a next, right? So I need to say, okay, my last then's last's next is a new node, given the data, right? So add something after my last, then I'll change my last equals last.next, and number of items, oops, shoot. I'm doing this in the wrong function. Don't want that. This one here. So this last's next is a new node, and then my last will change to my this last's next. Right? So add something after the current last, and then change where last points. If I added something after the current last here, last is no longer this one, last is now this one. Right? So now this one's no longer null here. Its next is no longer a null pointer. It has a value. That's how we add to the end. So go to the current end, add something after it, and then your last is now the new thing that came after it. So I can quickly add to the last here. My number of items goes up by 1. Removing. Now, this is all pretty well and good, so pop now. Do we want to take the first item or do we want to take the last item off? I think usually we take the last item off, right? Now, that one gets really tricky to take the last item off, because I don't know what comes before the last item. If I only know the first and I only know the last, I have no way of changing last to go back one. Right? I can only ever go forward. I can only add after it. I don't know what comes before it with a singly linked list. So this gets to be problematic. Well, turns out we can fix that too. Right? Instead of having single links, the next thing we can do is we can have double links. I can link to what comes before me and what comes after me. We can have a doubly linked list. Right? So my node then now doesn't just have the next, it'll have a node t pointer of the previous. And we'll say, hey, the node t pointer previous, we'll assume it's probably a null pointer until you tell me otherwise. So this previous is the previous. So I can have the linked list will tell me which comes after it and what comes before it here, which is really fun. So now when I make new nodes, right, your first item has nothing before it, has nothing after it. Easy. When you add an item to the end here, when I make a new node, the thing that comes before it will be the current last here. So I need a null pointer for next, but then the previous will be my this last. Right? So to make a new last, it has nothing after it, but the thing that's before it is the new last, or the current last. Right? So if I want to go add in, say, a 7, let me draw this again here. So we had 4, we had 3, we had 2 here, right? And now I've got 2 sets of pointers. 4 has nothing that comes before it. 3, I did not give enough space here. Sorry, one sec. 4, draw my boxes first. 3 and 2. Right, so 3 knows what comes before it, 4 knows what comes after it. 3 knows what comes after it, 2 knows what comes before it here. It has nothing after it. So I have double links here. So 4 is the first here, first, and 2 is the last. So I can find the first, I can find the last. So when I go to add another node after last, right? So I'll go add a new node here. We'll add it, say, like 7. The thing that comes before it is this one here. I have to say this one now comes after it. This one here. This one has nothing after it. So I can set the last here. So now to pop something off here, I wanted to pop off the last item, right? So we're going to take last's data, and then we had an old last was the last. Now we're going to change the last value, right? So my last was going to equal last's previous. Right? Go back one here. I can delete the old last, right? And then I can say my last's next is a null pointer. So if I want to take off the last item here, right? Save the 7. Say, okay, hey, thing that came before you is now my current last. So last will no longer be 7. It'll be last previous, which is the 2 here, right? So now last points back to 2 instead of the 7. Then we're going to go delete that one and take away the number of items and set last's, the new last's next, right? Break this link here. Get rid of this one here. It has nothing that comes after it as we go. So I just need to break those links to pop off my items as I go. Now first never changes when I pop off the last item. Right? It's only the last is changing. Eventually, I'm going to pop off the first item as well. So I have a weird case where once I remove the last item, when last is also the first item, right? When I delete it, it's going to be gone, but I won't know that it's a null pointer. So probably better to check on that before I just go delete what it's pointed at. So I can check real quick. Say if last is equal to first, then first equals a null pointer. Right, just to make sure that I'm cleaning all this up here. So if I get all the way to where I've added a bunch of items and I shrink them all back down, or if I've only added one item and I pop that one off, last and first are the same one, make sure that they're both going to be null pointers. Right? I don't want to run into any issues with that as we go. And now, this won't actually work if there was only one item here. This will crash here because last, when that's a null pointer, right? My previous was a null pointer. I can't set the next value of a null pointer. Right? This will crash on us here. Right? Right access violation. There is no last because it's a null pointer. So I only want to do this if last does not equal null pointer, which is a little bit obnoxious, but that's okay. So if last is not a null pointer, then I'm good to go. But now I can get my items off. 432. Now, interesting, we got them in the same order when we were adding to the first and taking them off from the front, but now we're adding to the back and taking them off the back. So it's still 432, but we're adding to the end as we're going here. This is a little weird here. It's okay. This is a lot. This is a new way of thinking about things here. But again, what's fun with these here, right? Regardless of how many items I have here, that big O performance here, on average, will always be a constant number of operations. Even if I have 1,000,000 items in my linked list, or if I have 3 items in my linked list, it's always constant. Right? I don't have to go find this particular value anywhere. So even the worst case will be O of 1. You know, we usually care about average, but worst case is O of 1. To add an item is still always O of 1 for worst and for average, because there's never any resizing that has to happen. This thing is always fast to add here. So you get pretty good performance on these things. Size is really easy. That's O of 1, right? We don't have to go count them at all or anything like that as we go. So it gives me a really quick data structure that will never be slow for adding and removing items, unlike vector, which has to do that doubling occasionally. Okay. Now, this gets to be a little bit messy, having to track the first links and last links and checking for null pointers and that sorts of stuff, right? This is not the cleanest here. It gets to be a little bit awkward. So there's a way we can make this even easier for us, so I don't have to deal with checking for nulls, which is super fun. So to do that, there's a trick we're going to use. Let me do another page here. So what I'm going to do is when I make a linked list here, right, linked, that's a D list here. I'm going to use something which is a dummy node here. So the dummy node has nothing here. It's just a whatever. And then it has a previous here. The dummy node's previous will always be the last item. The dummy node's next will always be the first item. So this way I will always have a node that exists. So if I follow my links here, I'll never get a null pointer, because I'm going to make this into a circle now, right? If this is always the first and this is always the last, I now have a circle. It's a circular doubly linked list here. So if I wanted to add in 2, right? Add in the 2. So first is 2. What comes before 2 is the dummy node. What comes after 2 is the dummy node, right? This is the last. It's also the 2. So right now it's just a circle with 2 nodes, the dummy node and the number 2. Right? If I want to add another node to it here, right? If I want to add after 2, I'm going to break my links here and say, okay, something that comes after 2, let's add the 3. What comes before 2, I'm sorry, what comes after 2 is the 3. What comes before the 3 is the 2. What comes after the 3, let me scroll down a little bit here, is the dummy node. And what comes before the dummy node, what is the last item, is the 3. Again, it's a circle. It's just a little bit awkward, the way that we're pointing at everything here. We're keeping the circle. So I will always have a node. And I promise this is a little bit simpler here. So let me actually just make a new file here. So let me make a circular doubly linked. I should have kept the singly linked list here, sorry. That's it. So just if you are bored enough to compare them. All right. So I've got a node, so I don't need to track first and last. I just need a node pointer for the dummy node. Here as we go. And when I create my linked list here then, I can make it empty if I want, which sort of makes this life a little bit easier for us here. So we'll say, hey, let's just start with no items here, and we'll take my dummy node equals a new node, right, because it's going to be a node pointer, and it has nothing here, right? And it's whatever t is. I don't know, like it'll just be a null. I think I can give it null. No, shoot it, because it doesn't have the data. Shoot. It might need to be a pointer to point at the data. I'm trying to remember now, because I can't have a t for none. Oh, we'll try. I won't like pointer. How do I give it blank? All right, we'll just take some t data then. That's fine. T. No, shoot, because I need something here. Node of t. T? Can you give it t default? I might be able to do that. It's a default t, and I have a null pointer and a null pointer. Then I'm going to make dummy node point to itself. So dummy nodes next will equal the dummy node, and dummy nodes previous will equal the dummy node. Right? So all by itself, it's a circle pointed to itself. Its next is always the first thing, and its last is always the last thing. When it's empty, there's nothing here. But now to add an item, I don't have to do any of this null pointer weird nonsense stuff here, which is super cool. So what I got to do instead, to add something to the end here, and we can call this like add last, to be specific here, the last item will come before the dummy node. Right? Dummy node's previous is always the last thing. So I can say I want to make a new node, so we'll have a node pointer for new node, new last, equals a new node of t pointer, and it takes the item. Its next then will be the dummy node, right? Because your last item's next is the dummy node to complete the circle. Its previous will be the current last thing, which is the dummy node's previous, right? So I put it in. Now it points to the dummy node. Now I need to tell the dummy node, hey, your previous' next is the new node, the new last. Right? Hey, thing that comes before you, I'm putting something after you now. Which gets a little crazy trying to follow these links here, but hey, thing that comes before you, 3, you have a new thing that comes after you. Right? I'm putting a new node here in the link here. I'm going to put a new node here of 4. Its next is the dummy node. Its previous is the dummy node's current previous, right, which was this one. Right? And I said, okay, dummy nodes, your previous next is me. So I will now come after that one, right? Put myself into the list here. And then, hey, dummy node, your previous is now me. Right? I put myself into the list here. Now, this gets to be a little bit awkward looking here, and turns out we can not have the same code twice. We'll fix that up in just a minute here. So we'll have an add last, and then we'll have a add first for a t item. Now to add a first item here, works the exact same way, except now we have a new first. So with a new first, what comes after it is the dummy node's first. Right, the dummy node's next. And what comes before it is the dummy node. Right, if I'm going to add to the front of the list here, I go between the dummy node and 2. So my previous is dummy node, my next is the dummy node's next. Right? My previous is the dummy node, my next is the dummy node's next. Then, hey, thing that comes after dummy node's previous is now me, the new first. Right? Hey, 2, you came after the dummy node, I come before you now, not the dummy node. And then, hey, dummy node, your next is now me. Right? Now, it feels bad. It's not exactly the same code here twice, but it's basically the same code twice. Right? So what we could do if we wanted is we could add a function, right? Because if you have the same code twice, that just the variables are just a little bit different, right? We should turn that into a function. So I can have a private function here for add between. Given a t for data, a node of t pointer, we'll call this one the next, and a node of t pointer previous. So to add between two nodes here, we'll go make a new node, right? So we can say node t pointer to add equals a new node of t given the data, and then its next is the next and its previous is the previous, right? Pretty quick and easy here. And then I have to tell what comes before me that I come after it, and I have to tell what comes after me that I come before it. So I can say my two adds, next's previous equals to the to add node, next's arrow previous. Right? Hey, thing that comes after me, I come before you now. And to adds previous, next, is the to add. I should say node to add, shouldn't I? Let's say node to add. Or should I call that new node? I'll call it new node. Yeah. That was the rename. Don't do it yourself, right? Use the tool, right? So make a new node and put yourself between this next and previous node. Right? And then tell the node that comes after you, you come before it. Tell the node that comes before you, you come after it. Put yourself into the list here. And then take my number of items plus plus. Right? So to add between then, to add last, I'm just going to call add between, given the item. Now what comes next? So if I'm adding to the last, the next thing then is the dummy node. And what comes before it is the dummy node's previous. Right? To add to the first here, I'm going to add between the item. Well, what comes after it? Well, that's the dummy node's next. Right? Next is always the first thing. What comes before it is the dummy node. Right? Now we have the same code twice, but we have a function for it. So where we feel a lot better about ourselves, right? You can always pop it off here. Or, I'm sorry, we can always just call add between. We just change where we're going between. We're either going between the last item in the dummy node or between the first item in the dummy node, right? Now, to pop something off, this is where it gets really nice and easy for us. So we can do pop, we could pop first, pop last. You want to do that? We call this pop last. So to pop the last item here, I don't have to go through all this nonsense, right? Because I don't need to worry about null checking. I will never have nulls, which makes it super nice. Right, so to get the last item, that will always be, so this is my T for data, is the dummy node's previous data. Right, dummy node's previous is always the last thing. Now, I probably do want to check, we did exceptions already, right? Yeah, we did exceptions, good. So if my dummy node's previous is itself, or if number of items is 0, right? If dummy node's previous is itself, it's empty. Or if I have 0 items, I'm empty. So I'm just going to double check. If my number of items is 0, I'm going to raise or throw error. What is it? Index exception. Oh my goodness. Where do I get all my exceptions? I have to go look it up here. I can never remember. Where's my exceptions? Here's my throw. A runtime error, sure, why not? Runtime error. List is empty. Do I have to include error or something, or does that just work for me? Include standard exception, there we go. Yeah, we haven't done that in a while. All right, standard exception, runtime error. All right, I didn't pick it up yet, but maybe it will. All right, so if we're empty, right, bad stuff happens, that's all. Otherwise, I know what the data is here, right? I've got the previous's data. Then I need to remove a node. Now, if I'm going to pop from the last and pop from the first, removing a node is the exact same process, right? I just need to know what comes after, what comes before. So glad you thought of making a function for that. That's good. We're going to have a t remove. That will remove, we'll say this is the node of t pointer next, and the node of t pointer previous. So remove between, right? Between. Let's remove the thing between. If I tell you what comes next and what comes previous, I can remove, or maybe we'll just have the node, right? That's even easier. So node of t, node. There we go. We'll just call it remove. So if I tell you what the node is, let's remove it. So the t data then is the node's data. Then to take a node out of the list, we have to tell it what comes after it to jump it. We have to tell it what comes before it to jump it, right? So my node's previous next will be the node's next, right? Hey, thing that comes before me, jump over me. You now point to my next, right? Thing that comes before me is next. It's no longer me, jump over me. And then the node's next's previous. Hey, thing that comes after me, the thing that comes before you is my previous. Right? This jumps itself out of the list here. Then we can delete the node and return the data. Oh, take our number of items, minus, minus. So if you want to pop the last then, we're going to return remove dummy nodes previous. Right? That'll remove the last item. Dummy nodes previous is always the last thing. Let's go get rid of it. Right? To pop the first, then it's dummy nodes next. The rest of the code's the same. Right? Remove the thing that was first. Take it out of the list here. And these are all constant time operations, which is awesome. Right? No matter how many items I have, it's only one operation. So let's see. So let's make a circular linked list here. So this will be our include circular doubly linked list here. So a circular doubly linked list of int. Circular? Did I do it wrong? Did I not rename it? I didn't rename it. Circular doubly linked list. There we go. It helps if you name these things, right? Okay, so now I got my linked list here. This is my circular list. And I can add item. Now I want to add, oh, is it just, oh, circular list here. There we go. Now do you want to add first? Circular list. Come on, dot. Did it make a circular list? Dot. Oh, must have a type. Int. Expression. I broke it. Circular list. Circular list. Dot. Dot. It's unhappy with me. What did I do? Local variable is not initialized. Call its constructor, right? Dot. I broke it. I don't know. I will fix that for you. We got 10:45. We'll figure out why it's not working in the main here, but we're good from here. So we'll play more with linked lists on Thursday. Believe it or not, they get more fun than this. Okay? All right. I'll see you for lab this afternoon. We'll have some fun. Thanks, everybody.